fine-tuning evidence. So we're presenting evidence to support the claim that in the set of possible physical laws, parameters, and initial conditions, the subset that permit life is very small. So first, let's look at examples of how the laws of physics themselves need to be just right in order to support life. But before we do, I think it's important to keep in mind a couple of caveats. We're not claiming to try to be able to evaluate all possible laws to assess the fraction that would be life permitting within that kind of infinite range. That would be clearly impossible. Although I think we do have some interesting data points. For example, the development of Conway's game of life, something which was discussed in the Barnes-Lewis book, A Fortunate Universe. They pointed out how it's been discussed that there was a lot that had to be just right, even in setting up the rules for this cellular automata situation, which would be a lot easier, of course, to do interesting things in than for biological life, where you also need to, for example, harness energy from the environment and things like that. Whereas if you're just running a program on a computer, you already have this environment in which you can try things out. So it's a little bit easier than life, I think, and not the kind of life that plausibly God would want to create. But even in this case of just life kind of happening on a computer, it was very difficult to set up rules that would lead to interesting kinds of things happening. So one quote from a review of this that was cited by Barnes and Lewis was the following. They pointed out that acres of squared paper were covered, and he, Conway, and his admiring entourage of graduate students shuffled poker chips, foreign coins, cowrie shells, ghost stones, or whatever came to hand until there was a viable balance between life and death. So it seems hard to get something interesting even in that context. But rather what we're going to look at in the fine-tuning for the laws of nature are just to examine a few minor tweaks to current laws that presumably could have been the case, but would have been disastrous to life. The combined level of improbability for all of these is going to end up being less than just for some examples of our finely tuned constants. But nevertheless, I think it's worth exploring a little bit about this evidence as well, and perhaps we can at least get some modest evidence for the overall claim of fine-tuning. So one example of fine-tuning of the laws, or at least just coarse-tuning of the laws, if you will, would be to examine the fact that atoms need to have quantized orbitals for the electrons, else they would be unstable. If you didn't have quantum mechanics, the electrons would lose energy to electromagnetic radiation and spiral into the nucleus, and all of this would happen in less than a nanosecond. It's also required to have stable chemical properties, that you have this kind of quantization, else the chemical properties of a molecule or an atom would be sort of dynamic and dynamically changing over time, depending on the distance of the electrons from the nucleus and factors of that nature. So think about how if your chemical properties, for example, of maybe the food you ingested, could change so suddenly, how it could all of a sudden be extremely bad for life. You might have eaten something which seemed to be perfectly good for you, and yet it could kill you because the properties changed into a toxin. So you need stability for life. A second example would be to think in terms of the Pauli exclusion principle, which is what prohibits electrons from all going to the lowest energy level around the nucleus. If electrons were bosons rather than fermions, they wouldn't obey this principle, and there would be no chemistry because everything would just be at this lowest level. You wouldn't have these complicated, interesting orbitals and interactions of atoms within a molecule and things of that nature. Also, we could consider, what if gravity were repulsive rather than attractive? Well, then you wouldn't even have matter clumping into complex structures. Think about the fact that your density is 30 orders of magnitude greater than the average density of matter in the universe. 30 orders of magnitude, of course, being a factor of 1 with 30 zeros after it. Or consider the range of the forces. If the strong nuclear force were a long range rather than a short range force, then there would be no atoms. The only structures formed would be uniform spherical lumps that couldn't really combine in interesting ways. And in order to have life, we do need to be able to do things like store and replicate information. And seemingly that would be impossible if you had the strong force as a long-range force, because then it would just dominate everything, being the strongest force. Another example would be to consider that if in electromagnetism like charge is attracted and opposites repelled, then once again there would be no atoms, only undifferentiated lumps of matter. Or what if you didn't have electromagnetism at all? All matter then would be sort of like dark matter, it forms these large, diffuse, sort of roughly spherical halos of matter. It actually does play a useful role in galaxy formation, does this dark matter, but it doesn't do anything like chemistry. It's been very elusive for us to nail down even the detection of what are these particles, which we call dark matter, because they just don't really do much. How can you store information or accomplish things like replication of that, such as you would need for life? Doesn't seem possible without electromagnetism. So Robin Collins has documented about 24 qualitative ways like this and argued that perhaps each one of them is, say, roughly half a chance of getting the law right. In many cases, you're choosing between two alternatives, and so that seems to fall out pretty naturally as a rough estimate. So if so, then you could say, well, the overall improbability of getting all 24 of these right would be 2 to the 24th power, which is about 1 in 16 million of a chance. So you do get something which still seems pretty improbable to have just happened. And that's the odds very close to winning certain versions of the lottery.